All right, the mole, 2,2. Please, 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 please read this. This is unbelievably important. The only number you put with the unit atoms, molecules, ions, the little things, is 6.02. They go together. The only number you put with the unit grams is something found on the periodic table. The only number goes with the unit liter is 22.4, and the only thing you put with the mole for now is a 1. So keep that in mind when you're doing the conversion factors in the dimensional analysis problems. The other thing you have to remember is that 1 mole of a gas, if it's a liquid, you can't use this. If it's a solid, you can't use this. It's only for gas. 1 mole of any gas takes up 22.4 liters of space as long as the conditions are certain things. We call these STP, specific temperatures and pressures. They're the standard values. So standard temperature is 0 Celsius and the standard pressure is 1 atm. Remember, if you put a balloon in the oven, it's going to get bigger. If you take a balloon outside and it's lower than, the temperature's lower than 0, it's going to get smaller. If you take a balloon and you increase the pressure on it, it's going to get smaller. If you decrease the pressure, let it float up, it's going to be bigger. So the volume and the temperature, or the volume will change if the temperature and the pressure change. But as long as it's at standard temp and pressures, then it's going to be 22.4 liters. We're going to deal with this quite a bit when we talk about gases, but you have to know it's set to the standards for now. All right, how many particles are in 1 mole? It doesn't matter if we're talking baseballs, if we're talking about peanuts, if we're talking about atoms. If you have a mole of something, it's 6.02 times 10 to the 23rd. Just like if you had a dozen, doesn't matter if it's baseballs or peanuts or atoms, a dozen would still be 12. A pair would still be 2. A mole is 6.02 times 10 to the 23rd. It's a lot. Where can you look to find the mass of 1 mole? The masses of 1 mole are on the periodic table. So now let's use the periodic table to figure out the mass of 1 mole of these following substances. Now you got to look at the subscripts. So oxygen, there's 2 of them. Don't miss that subscript. So it's 16.0, because that's what one of them weighs, times 2. So that's 32.0 grams. Here we have 1 calcium. Calcium's 40.1. We've got 2 oxygens, because there's 2 sets of hydroxide, OH2. So there's OH and OH. There's oxygen, which is 16.0, and there's 2 of them, so that's 32.0. And then there's hydrogen, and it's 1.0, and there's 2 of them, so that's 2.0. So if you add this all up, the 40.1, the 32, and the 2, you end up with 74, let me change my font or my color here, 74.1 grams. And finally, this crazy looking one. We've got nitrogen, we've got hydrogen, sulfur, and oxygen. There's 2 sets of NH4. So there's NH4, NH4. If you get confused, you're not sure, does a 2 go to the N and the H, just draw it like this. Draw 2 of them because of the 2. So there's 2 nitrogens. They're each 14.0. 2 times 14 is 28.0 grams. There's 8 hydrogens. 2 goes to the 4 also. So there's 4 and 4, that's 8. Hydrogen's little, it's only 1.0, so that's 8.0 grams. Sulfur, there's no number following sulfur, so it's just one of them. And sulfur's 32.1, 32.1. Oxygen, there's a 4 after it, so there's 4, and it's 16 for one of them, so that's 64.0 grams. Add all these guys up, and one of them weighs 132.1 grams. So that's 1 mole of ammonium sulfate. 1 mole, the molar mass. Now this question says, what's the mass of 3.4 moles? I know 1 mole, if I look on the periodic table for carbon dioxide, carbon's 12, oxygen is 16.0 times 2, so that's 32. 12 plus 32 is 44.0 grams. This equals 1 mole. The question says, what's the mass of 3.4 moles? So I'm going to use dimensional analysis. 1 mole goes on the bottom because I want moles to cancel. I know the periodic table tells me 44 grams is the mass of 1 mole. So 3.4 times 44, and you end up with 140.8 grams. So that's the mass of 3.4 moles. How many molecules are in that sample? I don't care that 1 mole weighs 44 grams. Doesn't bother me at all. It has nothing to do with this problem. This problem says how many molecules. I know that mole goes on the bottom. 1 goes with moles. 6.02 times 10 to the 23rd goes on top, because that's how many molecules are in 1 mole. So 3.4 times this, 2.05 times 10 to the 24th molecules. Remember, putting in scientific notation, never ever ever hit the times 10 button. It's EE, or second function EE. All right, what's the volume of this? Well, it's carbon dioxide, it's a gas, so I can use that 22.4 liter conversion factor. Now, it doesn't ask me about mass. I know 1 mole weighs 44 grams, I don't care. I know 1 mole has 6.02 times 10 to the 23rd molecules, I don't care. All I care about is the volume. Mole goes on the bottom. For now, 1 goes with mole, and 22.4 always goes with liters. That's the space that 1 mole takes up. But I have 3.4 moles. So 3.4 times 22 is 76.2 liters. So that's how much space 3.4 moles of carbon dioxide will take up. As long as the temperature is 0 Celsius and the pressure is 1 atm. Okay. If I make it warmer or colder or more or less pressure, that 76 is going to change. Now, which is going to have a greater mass, a sample with this many atoms of mercury or a sample containing the same number of molecules of fluorine? Now, they're the same amount of atoms. All I have to do is look at the periodic table. If I look at the periodic table, mercury, 1 mole of mercury, has a mass of 200.6 grams, or AMUs. If it's a mole, it's grams. And if I look at the periodic table, F2, it's 19.0 times 2, so that's 38.0 grams. So 1 mole weighs way more of mercury, weighs way more than 1 mole of fluorine. So it doesn't matter if I have a mole or if I have less than a mole, which I do here, slightly less. This is still going to weigh more than that because of the same sample size. So the periodic table is really neat because it helps us compare the sample sizes and the masses of everything. All right, determine the mass of 50.0 liters of oxygen gas. I want to know the mass in grams. So I've got to get rid of liters, and I'm going to go to the mole, and then I'm going to get rid of moles, and I'm going to go to grams. So liters cancels, moles will cancel, and I'll be left with grams. Now, some things I know. I know 1 always goes next to the mole. I know 22.4 always goes with liters. And I know I got to look on the periodic table anytime I see grams. So the periodic table, oxygen weighs 16, and there's 2 of them, so that's 32. That's how I know what number goes there. Do the math, and you end up with 71.4 grams. The next one, I've got helium here. I'm going to put grams here because I want grams to cancel. I'm going to put moles there because I want to get rid of moles. I want to go to volume ultimately, so I'm going to put liters there. And then I'm going to put moles down here so they cancel, and I'm going to put liters up top. Now, what do I know about units and stuff, or numbers? I know 1 always goes with the mole. I know 22 always goes with liters. And I know to look on the periodic table anytime I have mass. So helium is 4.0, so that number goes there. So grams cancels, moles cancel. I'm left with liters. All that's left is to run the numbers. So 24.5 times 1 divided by 4 times 22.4 is 137.2 liters. So 24.5 grams of helium, if that's what's in your balloon, then you have a balloon that has a volume of 137.2 liters, which is a pretty big balloon. We're probably not going to come across that in our normal birthday parties. All right, molarity up next.